que ahora está en Estocolmo, en Stockholm University. Es un exalumno de la Complutense y de estos departamentos nuestros, y todavía tiene ganas, como habéis visto, de acercarse. Y bueno, es un placer tenerlo hoy aquí, y empezamos cuando quieras. Empezamos, José. Bueno, José nos va a hablar de banda ancha, ¿ok? Y vamos, cuando quieras.
Vale, muchas gracias, Carmelo. En inglés, ¿no? Supongo que gente que... Sí, sí, sí. Okay, so thank you very much, Carmelo, for this invitation. I'm super happy to be here again in my alma mater, in the Complutense University. I'm a former student. I did my bachelor here, so I'm super happy to get the invitation. So I'm going to present this paper that is joined with Rosa Sanchez-Warner from Queen Mary University and Felix Weinert from Berlin. That is going to be about what is the causal effect of high-speed internet on student performance. So this is kind of a topic that is now quite hot in the daily basis, right? So let me start motivating this paper just by putting you into context. So if you think about over the last 2 decades, technological advances in information and communication technologies have dramatically changed the educational landscape. So nowadays, the educational technology industry is booming. So this industry can be defined as edtech or edutech, and here can be defined as any ICT application that aims to improve education environment. So here you may think about e-learning platforms, distance learning tools, massive online open courses, so the so-called MOOCs, or any software or hardware that you can think about. So in these days, most researchers, policymakers, and educators agree on the importance of incorporating these technologies into the learning environment. But however, as Escueta and Coautos 2017 highlights, still researchers and educators are far from consensus on what type of these technologies are most worth investing and in which context. Just to summarize, basically, we know we have to incorporate these technologies into the learning environment, but we don't know which ones are better and in which context can be more efficient. So one crucial ICT is the internet. And the internet nowadays is used for educational purposes at the schools, but not only at the schools. This is also complementing classroom education with additional online learning at home. So if you think about the home internet, so the effect of the home internet in student performance may be ambiguous. And this is due to the fact because on the one hand, home internet can increase learning productivity and widen educational opportunities, but on the other hand, it can also lead to unproductive distraction, right? If the students are every day just playing video games or working with the social media. So in all of this context, identifying whether high-speed or broadband internet impacts student educational outcomes has very important economic and policy implications. And this is basically by 2 factors. So first is because online learning is likely to remain as a key input in the educational system. And the most conservative estimates is saying that this is considerably growing in the future. And also because it's going to be crucial in the advent on temporary shocks. And here, one example that we have all in mind is just the recent pandemic COVID-19, in which many countries had to close the schools for several months, and basically home online learning became pivotal. So even though understanding this relationship between high-speed internet and educational outcomes is a first-order empirical question, there are major challenges that have limited the scope of previous research. So basically here we distinguish 2 kind of empirical challenges. So the first one is what we call as active selection. So this means that observed home internet speeds are non-random. So they are a product of different choices made by the individuals. So one obvious example is that you can think about that relatively richer parents are going to be more likely to buy faster packages, broadband packages, and also better equipment. So they are going to be more likely to buy a better computers or a better modem that is going to increase the observed internet speed at home, right? So basically, we just do a simple relationship between packet internet speed and educational outcomes. This regression is very likely to suffer from selection bias. So the alternative that we have here, or the potential solution, is to use the infrastructure. So basically, we are going to use local available internet speed as a proxy. So here we are going to use a telephone local exchange, which basically provides telephone and internet services to the households. through the DSL technology, through the digital subscriber line technology. So this is the context. So instead of using the observed speed, we are going to tackle active selection by using the local available speed. And then the second empirical challenge is the passive selection. So basically, this local available speed is going to be determined by the distance from the household to the local exchange station. So here, basically, there is a property from the Internet Copper wire cable that all the DSL, so ADSL and DSL technologies have in common. That is that the closer the household is to these stations, the faster the internet. And the farther away, the slower the internet. So this is an internet decay on the distance to the station. So basically, seems unlikely that the households are going to actively sort nearby these close locations because of the DSL technology. But the thing is that these telephone exchange locations are not going to be randomly allocated through this space. So basically, they are more allocated in the central locations, near to big buildings, etc. Because basically, what in the deployment of these stations, what they wanted to do is maximize the number of people covered, minimizing the number of stations. So basically, we are going to compute the distance between the household and this station. This is going to be suffering from selection bias. Especially, what we are more care about is then observed characteristics that are going to be affecting our outcome of interest that matters for household sorting. So this is what we call passive sorting. So basically, estimating causal effect of high-speed internet on educational outcomes, you can see that it's non-trivial. And to estimate those causal effects requires an identification strategy that overcomes both types of selection. So this paper in a nutshell. So what are we going to do in this paper? So the goal of this... Yeah.
May I?
Please.
How does this distance decay compare with other sources of... Are you going to tell us?
Yes, so you mean like with other technologies or other internet technologies?
No, I mean compare with congestion or other sources of decay of the quality of the network that are different to distance.
Exactly. Yeah. So I mean, this is a very good point. So basically, the observed speed is going to depend on many factors. It's going to depend on the computer you have at home, the time of the day that you are using the internet, as you were saying, also the congestion. So this is going to decrease your speed. But basically, what we are going to look at here is a proxy for this observable internet speed. That is basically whether consistently you're going to be closer or farther away from the station, and this is going to provide you with higher or lower speed. I'm going to put you a little bit more into context now in the background, if you want, but
okay, no, go ahead.
Okay, thank you. So basically, what we are going to do this paper is to estimate the causal effect of home internet high internet speed on teenager test scores. So just to be clear about that, we're not going to estimate the effect of having high-speed internet versus not having internet, but increasing the quality of the high-speed internet. That's what we are going to be estimating. So the context of this paper is the universe of 14-year-old English students in a national test over the period 2005 and 2008. And basically, we have different databases, but just to put into context, we have three main databases. We have administrative data on the universe of students' standardized test scores in K stage 3 that I'm going to explain a little bit after, but basically this is the standardized test performed with 14 years old. And basically we are going to have a lot of background characteristics to control for. One particular one that we particularly like, that is the pre-internet standardized test scores. Basically we can control by the predetermined standardized test score of the student before the high-speed internet was introduced. We have also telecommunication network data. So we have the universe of English local exchange stations, which are about 4,000 in the whole England, and also the assignment to each of the roughly 1.5 million full postcodes. So we are going to use in this paper the postcode level data, which is the most disaggregated level in terms of the location of residences, which just for you to think about is about 15 households. And in some very urban and dense areas, they are about one building. So that's for you to understand what we are looking at. And we are going to have also plenty of georeference control variables that allows to compute residential proximity to a comprehensive list of local amenities. And we are going to use this just to address for this passive selection. The empirical strategy that we're going to use is a spatial regression discontinuity design, which basically what we are going to do is, in order to avoid this passive selection, we are going to focus on the invisible catchment areas of each of the local exchange stations, and looking at students that live very close to each other, but one is covered with one station that have longer cable, another is covered with other stations that have lower cable, so higher speed internet. So that's a bit the idea. And the main findings, yes, sorry.
José, may I make you a question?
Please, please.
So what kind of mechanism do you have in mind to explain this relationship?
You mean like the relationship between internet and student performance, right?
Absolutely, yes.
Yeah, that's a great point. I mean, that's actually one of the key points of the paper. So one of the limitations of the paper is that we are not going to be able to look at the direct mechanisms, because survey data cannot go as decentralized as we go in our main empirical strategy. So this is a limitation of the paper, but basically what we have in mind and what other papers have kind of done is whether higher speed internets allows students to enter and to look up for more information. So we cannot distinguish here between whether the effect is coming from, let's say, the extensive margin or the intensive margin. So meaning that if you have higher internet speed, you may go online more often because you have higher internet speed, or conditional on being on internet, you are going to spend longer hours because you have high internet speed. So in our context, the internet speed that is about 4.6 megabits, it's already enough to enter in web pages as Wikipedia, to download videos on YouTube. And basically in this period, we had plenty of educational platforms that were open and launched. So you can think about YouTube, that was launched in 2004. The Khan Academy, which is a very important educational tool, was launched in 2006. Wikipedia from 2004 onwards incremented the number of articles exponentially. And also social media was introduced in Microsoft Messenger. So there are like this plenty of resources that basically we think that this effect is coming from. I mean, what we observe is the net effect. So a net effect between whether students are getting more information and increasing their productivity, offset of this distraction effects. I don't know if this answers you, Luis.
Sure, yes, thank you.
Thank you very much. So just to give you the main findings of the paper, so for you that wants to sleep a little bit, so you know what we find. So we find that basically moving 1 kilometer closer to this local exchange station increase the test scores in 1.22 percentile ranks. And what we do is then award estimates to try to get the policy relevant parameter, which is the distance between the relationship between speed and test scores. And we find that increasing 1 megabit of the speed increased test scores in about 5% of the standard deviation. So this is our main findings. So let me go now, if I can, yeah. Let me go now just to show you a little bit about the related literature. So this literature, I mean, this paper is mostly related to all these papers related on the impact of broadband on different socioeconomic outcomes, showing positive effect of employment productivity, and negative effect on political turnout and, for instance, crime, sex. Also, there are plenty of papers on the impact of ICT in school settings, which are finding mixed results on educational achievement. So our paper is going to be different because we are going to focus on the home internet, the effects on home internet, not on the school. Also, this paper is mostly related with all these papers that are looking at the home broadband technology and see the impact on test scores. And basically, we are highlighting two that are the papers that are most related to ours. So the first one is Malamud and co-authors 2019, that they basically find no effect on a randomized control trial implemented in low-achieving schools in Peru, no effect on student achievement. And basically, our paper expands the paper of Malamud, identifying the effect based on a broader population that covers all socioeconomic levels of school-age teenagers. So basically, we are not going to focus only on low achievers, but we are going to look at other socioeconomic levels. And also, we complement this paper of Delling and co-authors 2018 that using data from the US, what they find is that those postcodes that have broadband access, those students that were in those postcodes, they were increasing their SAT scores, which is the exam in order to enter college in the US, but also to increase the number of applications to college. So basically that's go through information mechanisms. So we complement the paper of the link, analyzing the impact on a test that is going to be low stakes from the perspective of the student, and that is specifically designed to test cognitive ability. So basically we are not going to have these problems that they face on the paper about teaching to the test or whether students are developing online training resources. So the contributions of the paper are going to be 4. So the first one is that we implement an estimation strategy that addresses all the identification challenges that I was talking before. So it is active and passive selection sorting, but also attenuation bias that is quite striking that I'm going to show you a little bit later. So the second contribution is also that although our main estimates are coming from the relationship between the local exchange station, the distance to this station, and the student test scores, implementing a bold estimate, we are going to be able to underpin the relationship between broadband speed and student test scores, which is basically the relevant policy parameter in order to address policies interventions such as subsidizing high-speed internet or trying to increase the level of high-speed internet families. The third contribution is that our outcome variable informs us about the effect of learning and knowledge accumulation in the human capital classical way. So we are not going to have our outcome variables low stakes and no explicit training, so we're not going to have this teaching to the test or other kind of incentives. And the fourth is that we're going to, yes, sorry.
Sorry, a question.
Yes.
There is a distribution, right, I suppose. So there is a distribution of, and do you know something about the distribution rather than about the mean or just that?
So we are going to look at the effects on the, so basically what we do with the distribution is that we percentilize by subject and year. So try in order to compare our results with other papers in the education literature that do that. And we're going to look at the effects on the mean, on the average effect on student performance. Is that what you were?
I think it would be interesting to know what are the effects on different people, you know, so people who were doing badly before are doing now better, or is this kind of increase that you have in your paper due entirely to the fact that good students are now doing much better? If I were the referee of this paper, I would care a lot about this kind of effects, you know, distributional effects.
Yes, no, you are totally right. I mean, we are looking at different heterogeneous effects. I think that's what you were kind of wondering. So basically, we do the effects by gender, we do the effects by predetermined ability test. So we look at high achievers and low achievers, and we see that the effect is stronger in high achievers, but not statistically significant with respect to low achievers. And we also look at free school meal versus non-free school meal. But also one interesting thing of what you were saying is that maybe we can also look at the effect not only on the average effects, but on other moments of the distribution. That's what you kind of have in mind, right, Luis? Yeah, thank you, great. So yeah, so just to like the 4 contribution of the paper is that we are able to isolate the impact of home broadband on the student test score, abstracting from other school mediating technological factors that may affect the student performance, and that it's basically one of the main literatures that has been established. So I will show you why. So let me continue if I can move. Yes. So let me continue now with the background data and summary stats.
Can I ask one quick question? How can we read the main results? An increase, a decrease by 1 kilometer in the distance from the central, from the hub, and an increase by 1 megabit. How can I interpret that in terms of, say, standard deviation of the distance and megabit speed? Is it a big increase, a small increase?
Yeah, so
just to put the paper in perspective.
Yes. So it's about like 1 kilometer is about the standard deviation of, I mean, it's one standard deviation of our distance.
One standard deviation.
Yes.
Okay.
So just for you.
And what about one? And is it roughly in line with 1 megabit, or is 1 megabit?
So it's a little bit below. So it's about 0.9 megabit. So what we're going to do is compute the world estimate. So we compute the two estimates separately, and then we compute the world estimate and compute the standard error using the delta method. I'm going to show you a bit later, but this is the idea. So basically the distance is 1 standard deviation, and the megabit is a little bit lower, but closer.
Fine. And as a related point, so the technology is not uniformly spread. The ADSL technology is not uniformly spread spatially, and schools are not uniformly spread spatially either.
Yeah, so schools are not uniformly spread, but the technology is uniformly spread at the time that we have the data, which is from 2005 on. So this is what I'm going to say, that this infrastructure. Everyone has the infrastructure that is 99% of the English addresses are covered by these broadband telephone stations. So basically, like, the infrastructure is there, but then the take-up is in an increasing trend in that period. So the level of take-up.
What I had in the back of my mind is, what if different schools who are not uniformly located make differential use of technology in their teaching, in the, school production function? It's not a threat to your identification. I was a member of the identification police. I stopped. I resigned. From an economic viewpoint, is it interesting to think that certain schools cater for technology differently? Are you using it as a potential heterogeneous effect? Can we learn something from it? It's an open question. You take it if and when it suits you best.
No, that's a great point. I mean, I like identification police, Marcelo, so no worries about this.
It's Alberto Lesina's super point. I am a humble servant.
Yeah, so I think that's a super good point, the point of the schools. So in this case, for instance, our catchment areas of the stations do not coincide with the school catchment areas. And in that way, what we can do is to control by many school technological factors, because we know which school are assigned students to. And also the most saturated identification that we do is that we control by a school fixed effect, which is just like absorbing all of the potential effects that are coming from the school. And we find that it's still the results are significant and pretty much the same point estimate. So I will show you a little bit later. But this is, I think, it's a super good point, because I would like to try to develop a bit further this interaction between families and school.
Because I think it's economically beyond. It's economically more relevant than just doing the due diligence you do to look at fixed effects. We all know that that it is not just broadband, but it is how a school complements the access to broadband, which can make a difference, rather than developing couch potatoes. I'll close on this. Go ahead, sorry.
No, exactly. I think it's a great point. So I come back a bit later when I look at the heterogeneities, and we can discuss it further. So just to show you a little bit the background of how was the broadband expansion in the UK. So in the 1992, it started the dial-up internet access that was first introduced in the UK, which basically we had the speeds of roughly 40-50 kilobytes on average. And at the beginning of the 2000s, the rollout of the DSL broadband technology in the UK started. And now basically we define broadband as this technology that has a strictly higher of 500 kilobytes in speed. So the technological upgrades of the telephone stations. So basically these telephone stations were deployed during and before the World War II. And basically what we did is that they were upgrading this station in order to have internet access at broadband. So we have the full distribution of these stations, and each station has a different catchment area in the whole England, as you can see in this map. So the infrastructure, as I was saying to Marcello, was completely deployed in 2005, which is the first year of our paper. And then the take-up, so basically the broadband penetration into the households, was increasing exponentially after 2002. So for you to know about, so in 2005, we had about 30% of broadband penetration, and in 2008, 65% of broadband penetration. So in terms of external validity on the context that we are analyzing, we saw that the average connection speed in 2007 was 4.2 megabytes. So basically, with these 4.2 megabytes, first, this is going to be relevant in order to get access to the different educational content over the internet. So you can download videos in a reasonable time. You can enter to Wikipedia. You can enter to the online resources. And also, if we put into perspective with today, this is going to be still relevant in the world context. I can come back a bit later with this. So just to know a little bit more on the data that we have administrative student records. So the English educational system is performed in a way that in the English educational curriculum, there are 4 key stage tests that are called. So key stage 1 is devoted for students of age 6 and 7, key stage 2 for students of 10, key stage 3 for students of 14 years old, and then it ends up with the key stage 4 with the GCE examinations, which basically is the key stage 4, a student has to choose different certain subjects, and they have to do the examination with that. So we're admin data on the universe of the students enrolled in the English state schools, which are 95% of the population, that took this test between 2005 and 2008. As I was saying before, our main outcome variable is transformed into percentile rank, its test. This is due to the fact that we want to compare our effects with respect to the other papers in the literature. And we have also additional data on the student background characteristics, and most importantly, on the key stage 1 test scores for each student. So this test score that corresponds to the tests that were taken in the 1998-2001. So we can control for pre-broadband test scores by student. We have also average house prices and area socioeconomic characteristics. So basically, we have transaction level data on property sales in England. We have the universe of property sales in the whole England. Basically, local house price capitalized in the urban literature many desirable, but most importantly, undesirable local attributes and capture a large number of spatial heterogeneities and unobserved characteristics. So we are going to control by and compute the Euclidean distance between each English postcode and the nearest school, road, railway station, water body, and nearest supermarket. So these variables that has shown that has an effect on the educational content. And we are going to also compute the local density, calculating the number of premises in each postcode and the number of students. So regarding the postcode broadband speed data, so we use additional data on postcode level realized internet speed. So basically, one limitation that face papers that are using, looking at the effects of broadband in the UK and other countries is that there are no fine data on internet speed at a very disaggregated level. So basically, the first year that we have this disaggregated level is in 2012, in which they are published year at the postcode level on realized internet, which is about 1 million postcodes. So basically, what we do is that we compute average and median speed at the postcode level measures from what is called the modem sync speed, which is basically capturing the highest possible speed at which data can be transferred across the line with the use of a particular DSL technology. So basically, the highest speed that is sent the signal from the station to the resident. So this is how we are going to estimate the speed. So of course, the limitation that we have here is that the data of the speed doesn't correspond directly to the data in which we are estimating our main parameters, right? So after 2008, super fast connections started to develop, and also the 3G technology. So they may be confounding our estimates, but one of the positive things is that still in 2012, even though that the super fast connection were almost all the infrastructure were built, the take-up was super low. And still about 80% of the subscribed broadband connection use ADCL technology. So meaning that we have this signal decay in the coupled cable wire. So still, this signal decay is going to show us what is the difference on speed across the different boundaries of the stations. So that's how we are going to estimate the speed to do the world estimator. Any question about the data, or should I go with the strategy, more interesting things? Okay, so let me show you a roadmap. So about what is the empirical strategy and how we're going to do. If you basically know this, then you understand what we are doing. So in order to overcome all the identification challenges that we face and to estimate relevant magnitudes, we are going to follow 5 steps. First one is that In order to tackle active sorting, we are going to use a measure of local available speed, that is this distance to the connected station. In order to avoid for passive sorting, we are going to compare pupils across the boundaries of this station catchment areas. So basically those pupils that live very close to each other, but that are covered by a different station catchment area. In order to cope with the attenuation bias that I'm going to show you graphically now, we are going to use a fuzzy RD design using a dummy between fast and slow side. And then now we have the estimates of distance to the exchange and how is the effect on the student outcomes. But then if we want to take the relevant policy parameter here, we're going to implement and calculate distance speed estimate with the out of sample data that I was referring before, computing a world estimate. So basically we are going to here take the margin of what if I increase the speed, how my student test scores change. And in order to go and refine this a little bit more and to test and show the relevant magnitude, we're going to rescale our estimate using the population of interest, right? Because the population of interest here are English households that have kids in teenagers age, right? So those are the relevant population that we wanna test. So this is the idea of what we are doing. So in terms of empirical study, let's go graphically, which it's much more easy to understand. So this is a map of an overview of the local exchange catchment areas and the boundary segments. So basically you have this map of, can be a city in the UK. So each letter corresponds to a different catchment area. You can see these little and beautiful houses here that are referring to the local exchange stations. So those are the local exchange stations, and this A local exchange station cover all of this catchment area. So if we zoom in a little bit, we can basically cut these catchment areas into different boundary segments. So what we do is that we focus on these boundary segments, and then we have the students that live right on the border of this catchment area number A, and these students that live in the border of catchment area number D. So those students are going to be very similar in their observable characteristics, but what is going to be different from them is that students in the site A are going to be more farther away to the local exchange station, and the students from point D are going to be closer to the local exchange station. So this is going to be translated into a difference in the distance of the cable that goes to the station. So meaning that a jump in the distance to this station is meaning a jump in the speed. So basically we are going to call slow sites, so those sites in which you have higher distance, and fast sites, those sites that you have lower distance. And then if you look at, for instance, these guys here, so this is going to be a sharp design. So basically this is clearly farther away than this guy that is closer. So we are going to have a sharp design. But since it depends on the topology and the geography of the urban characteristics, we are going to have here an issue, that is that our design is going to be fuzzy. And this is due to the fact that you can see that this kind of line is diagonal. So this means that we are going to assign some pupils to one side, but basically they are going to have to be corresponding to the other side. So that's why our design is fuzzy. And that's why that if we use a sharp RD design, our estimates are going to suffer from attenuation bias. And this is quite cool, I think, and I'm going to show you a little bit later the sharp estimate. So you're going to see that it goes in the same direction, but a little bit lower.
Jose, may I say something?
Please, please.
There is this problem of in which when you have this kind of data, that there are sometimes severe spatial autocorrelation, right? Because you and I, we are very close, and in our houses, we are very close in everything. Do you take into consideration this?
Yeah, so, okay, so basically, so you are more thinking about, so just to understand your question, more on like maybe serial correlation or autocorrelation, let's say in the cross-sectional level?
It's not the cross-sectional, it's that the residuals are correlated, right? Because essentially you are taking things that are very close, right, in everything. And then there is a recent paper by a statistician in Ireland, Morgan Kelly, who actually claims that this is a big problem in other papers, not in the kind of papers that we have, but that you have to be careful here.
Right? Okay, I get your point. So as I was thinking on that, so basically we maybe can have a problem if there is some serial correlation. So if we are looking at the dynamics within these margins, but what we are looking at is exactly this dimension, because we are using boundary segment year fixed effects. So we are going to focus on the cross-sectional variation by year and within each of the segments. So this maybe reduce a little bit this concern. And also, one of the things that in observable characteristics, students are going to be similar. This is going to be one of the one of the strengths of our empirical strategy, because we want to look at students that have similar characteristics, but otherwise they are located at different distance. But I take your point.
I send you by the chat
send me the paper. Great. Thank you. So this is the main equation that we are going to estimate. So basically, here we have the test score of students in pupil I living in postcode P in the boundary segment neighborhood N that is associated with a given station and is attending a school and time T. So basically, this is going to be the distance to the station, and we are going to control by different observable characteristics at the student level. So specifically, this pre-internet score. We are going to control by, for instance, different school characteristics, so the distance to the school or the school type. We are going to control also by the time variant characteristics of the postcodes. So, for instance, we are going to control for the local housing prices dynamics in the postcode. We are going to also to control by the variant characteristics of the postcode, such as the density, the number of premises, and the distance to different amenities. And we are going to use here postcode time two-way fixed effects. So basically, the level of observation is going to be the one that I showed you in the map before. We are going to cluster our standard errors at this level too. And then we are going to use a flexible control function in the RDs that basically we are going to try to go as non-parametric as possible in that way. So we are going to estimate different bins. Bins are going to be on the distance with respect to the cutoff. So we are going to estimate in our baseline sample 100 meters bins, and then we are going to allow to these bins to vary. But basically, our results are consistent of using a continuous variable of distance or using different more parametric specification. And then basically what we are going to do is this distance, we are going to be estimated by this dummy on whether you are in the fast or slow side. So let me go now with the results. So basically some summary statistics of what we have here. So this is the whole sample that we have, which is 1 million students. And this is the baseline sample that we are going to take at those students that are living within 300 meters. And then in our robustness checks, what we do is we reduce this sample, we increase these boundaries, this boundary, and results are not statistically significant. But just for you to know that our baseline sample is this. So basically, you can see here that the observable characteristics of the whole sample are quite similar to those at the students that we are looking at the baseline sample. So in particular, the average house prices, or the number of schools, the distance to the school, the free school meal, which is an indicator of low-income student in the UK. So they are quite similar. So we have about 200,000 students in our main specification. So basically, in order to get a little bit with the internal validity of our paper, the first thing that we need to check is whether there is no endogenous sorting around the cutoffs that we are looking at, so around the catchment areas, boundary sector. So here, this is the histogram of a density estimate with a different distance to the cutoff. So the cutoff distance, the point 0 is this continuous line black, and then basically this is the density estimate. So what we see here is that so we are looking at very precise beams of 20 meters. So you can think that this is a very small very small measure. So what we are looking at is that there is a drop in the density right at the cutoff, but on the same magnitude in both sides. So analyzing the data a little bit, we basically think that this, just by data construction, and this is because this is 20 meters, which is a super low, super reduced distance. So since we are estimating each postcode, we have to take the centroids. So we think that that's why right at the cutoff it decreases, because if you add up these two, it gets exactly the level that we are having here. So anyways, just to be a little bit on the right side and don't go further with that, we're going to use a donut RD. So this means that these observations are going to be discarded for the main estimates. And also what we do is we develop the McGrady 2008 test and the Catania 2018 in order to test for manipulation at the cutoff, and it seems to look fine. So, but this table may convince you a little bit more, which are the balance of the baseline characteristics. So basically what we are looking at here is a bunch of observable characteristics at the student and at the area level. And we are going to see first whether these characteristics are important in order to determine the student educational outcomes. So this is what column 1 is showing to you. So those are local regressions of the observable characteristic on the outcome variable, which is the average percentile rank score. So this first column, what it's telling to you is that our observable characteristics are statistically but also economically meaningful to determine the outcome variable that we are going to look at. So basically what we are interested into discover whether there is some endogenous sorting in some kind of subgroups of the population is whether these characteristics are different right at the cutoff. And this is what column 3 is telling to you. So basically what we see is that there are few characteristics that by chance they are different, statistically significantly different at the cutoff, but we see that most of them are not, and they seem to be equal. And also a joint test of testing whether all observable characteristics are equal to 0 cannot be rejected. So this is the first stage of what we have. So this is the difference, this is the cutoff, and this is the distance to the local exchange station. So basically this is the first stage. So what we have is that two divergent trends, basically. So this is explained because as you go farther away from the cutoff, then the distance increase, right? And as you go closer, then distance decrease. So what we find is that this jump of about 800 meters, and this is the first stage that we are going to use, this jump on the distance to the station at the cutoff. So those are the main results. So basically, here you have the first stage in the panel A, and in the panel B, you have our effect on the National ICAE Stage 3 exam scores in percentile ranks. And then you have like these 5 columns are basically more saturated specification, including all the level of controls that I was saying before. So this is going to be our preferred specification. So you can interpret this coefficient as saying 1 kilometer closer to the station is going to increase the student standardized test scores into 1.2 percentile ranks. So this is our fuzzy estimate, but this is what I was saying before about the sharp RD. So those are the effects using a sharp RD. And then you can see that the effects are still significant, but the point estimates are 5 times lower than the fuzzy effect. So basically, if we don't account for this misallocation of the students, then we are going to have attenuation bias in our estimates. Yeah, I don't know if someone, Luis, maybe wanted to. No, okay. So those are our main estimates. So we develop different robustness checks. I don't want to go, for the sake of time, all out on that. So we test for the different distance to the invisible segment boundary. We try for different jump choices, clustering choices, and all results seem to be quite robust. But we do one thing that Marcelo was asking before, which I think is pretty nice to show, that is the sensitivity with respect to the school ICT technology, right? So basically, this is the hypothesis that maybe what we are capturing in this positive effect is not the effect of the home broadband on the student performance, but is more maybe the mechanism is driven through the school. So basically what we do here is that this is our non-parametric estimates, our baseline estimates. And then in this column 2, we include the school proximity to the station. So basically taking into account whether the school has higher speed internet or not, the months since the ADCL school upgrade, and we observe that the effect is still significant and the magnitudes are quite similar. And then we increase the level of saturation of the specification. We include the school local exchange station fixed effects. And then our most preferred and most saturated specification is this one, that basically including school fixed effects. And you can see that the point estimates get reduced a little bit, but basically this estimate is not statistically significantly different from the other one. So we can see that basically controlling by the different technological factors that may driven the effects of home broadband, the effects still are significant and with relevant magnitude. So now let me show you the, yes, please.
Sorry if I ask you something that you already said. When you refer to performance, what kind of performance is this in mathematics, in history, science?
That's a great question because it's really this slide, the next one. So it helps me a lot to answer you. So basically, we're looking at the average score over the three different subjects that are tested, that are English, math, and science. And that's when I refer to performance, we refer to the over average score. Basically, here what we look at is whether there is some heterogeneity in the subject. And we find the effect is stronger in English and science and stronger than in math. So math is not statistically significant, but when we compare these coefficients, we cannot claim that they are heterogeneous effect because they are not statistically significantly different to each other. So we also test for the heterogeneous effect by student characteristics, which I think was a bit of a question of Luis before. So whether there are some type of students that are more affected than others. And basically what we see is that the effect seems to be stronger for girls for high predetermined score. So basically here is dividing the predetermined key stage 1 test score into high and low performance. So it seems to be stronger for higher achievers, more stronger for white, and more stronger for non-eligible to free school meal. So basically for non-low income students. So this will go in line on what literature has found. So for instance, in the paper of Derling in 2018, they find that having broadband in your postcodes, the effect were driven by those white, urban, and higher educated families, and no effect for the others. And also it will go along also with the Malamud 2019 paper that is finding no effect for low achieving schools in primary education in Peru. But basically here we cannot push this very strongly because when we compare the estimates of high and low, they are not statistically significantly different. So basically we see that there is some sort of more strong effects, but they are not statistically significant, so we cannot claim further than that. And now let me go with the last part of the paper, that is basically reconciling our estimates and try to capture this policy relevant parameter between internet speed and test scores. So basically,
one quick question, Jose. You showed as main dependent variable key stage 3, right?
Yes, exactly.
Why not key stage 4?
So this is I have it in the conclusions that this is one of the extensions we want to try to do because we couldn't allow for the data at the moment. But what we want to do is, so first we wanted to try to get a test that is low stakes and basically not teaching to the test in order to capture the effect of what is called cognitive skills on the literature. So more like clean on that way. Because in key stage 4, since students have to choose between different subjects, there is more selection on who goes to one or the other. So we want to look not on the performance of key stage 4.
Look at key stage 4 English, maths, and science. Those are compulsory.
Exactly.
Then if you may take double science, you may take history. That's not compulsory, but
exactly.
The reason is with my papers with the same data, referees say key stage 3 is not as hardcore than exam as key stage 4 because it is an intermediate exam. It has been abolished, and if I remember correctly, when I had to look at the details, it is not as highly assessed, as externally assessed as key stage 4. But you may know the details better than I do. So look for key stage 4 right away. If you find an equally robust result, it means that there's a in the inverted commas transmission mechanism. Otherwise, it's a blip and we learn anything. We learn a lot, and nonetheless, talk later anyway. Sorry.
No, you're right. You're right. I mean, the reason why I didn't include it now is because we didn't have the data, but probably we are getting soon. So this is one thing that we have in mind, especially also to look at the key stage for selection of subjects, which is one of the things that may be important. So basically, whether you select more selective subjects, because they will go through this information channel in terms of content. But then, yeah, so in key stage 3, so this is basically this externally blind mark test. What we wanted to do with this test is that this is low stakes, right? So basically we are testing at something that are not going to be any confounding variable coming along, right? So if parents are helping more the students because this is a high stakes test, that is the case on key stage 4. So now let me go with the last part of the paper. What we do is that, just to remember you, we use this out of sample period data to reverse engineer the distance speed relationship present during our study period. So now we do this regression. So now the regression, you can see that the number of observations decreases, and this is because the observations are at the postcode level, not at the student level. And then we compute now the dependent variable, that is the average internet speed. And we see how this average internet speed changes at the cutoff of the catchment areas. And we control by different other characteristics and different dummy variables. And basically, our preferred estimate is this one, which is saying that 1 kilometer closer to the station is increasing in 0.9 megabytes the speed, right? So then what we use with this estimate is that we compute the world estimate between the beta causal effect that we identified before and the beta on speed. And basically what we find is that the world estimate is 1.37. So this implies that for each increase in the broadband speed of 1 megabit, test scores increase on average 1.37 percentile points, which is about 5% of a standard deviation in our grades distribution. And what we do is that the standard error of this world estimates is obtained using the delta method, estimated with high precision. So we have a p-value of lower than 0.01. And then in order to go and refine a little bit more this parameter that we use, we try to rescale our estimate for the broadband usage. And in order to do that, we use different kind of surveys that are available in the UK. And the most interesting one is the Oxford Internet Survey data. So basically, we have this administrative, this survey data, and we compute what is the broadband take-up for our study period group of interest, which is English household with home broadband at home that have children that are aged in a range between 14 and 17 years old. And basically, we compute that the household average broadband usage is about 70%. And this makes sense when we look at other surveys, and we rescale our estimates. That basically what we do is increase a little bit the effect to a 7% of standard deviation. So now just let me wrap up. I don't want to destroy you with my online speech. So just to wrap up the conclusions. So what do we learn from this paper? So in this paper, what we do, we implement a fuzzy spatial regression discontinuity design to estimate the causal effect of available broadband internet speed on test scores of 14-year-old pupils in England. The main finding of the paper is that increasing home internet speed in 1 megabit increase standard test scores in approximately 5% of a standard deviation. To put it into context with education literature, headline effect is not small we compare with the others. So feature effect, for instance, for giving you an approximation, are the effect with the highest or the largest, relatively largest impacts in the educational literature. So basically having a better teacher increases between 10 to 20% standard deviation. And then our effect will be more similar to those papers on peer effects that are estimated on effect between 1 and 8% of the standard deviation. And there is also that will be also higher than other kind of papers that have shown a neighborhood quality effect, that have a smaller effect on test scores. So in terms of the limitations of this paper, so the main limitation of the paper is that we cannot precisely pin down the mechanisms behind. So since survey data is low quality or is not as high quality as the data that we have, and as we cannot implement as a demanding empirical strategy as the one we are we are implementing using survey data in order to see what are the mechanisms behind. But basically what we can do is just to discuss what we think are the mechanisms, and it goes of what I have already told you. So basically through information, we cannot distinguish between this external validity, extensive mining effect or intensive mining effect. But what we can see is that in those years, many websites and educational resources were available online, and the relevant internet speed was okay in order to download these packages. So this paper also provides new insights in order to inform policy decisions that are related to investment in high-speed broadband networks. So basically, the goal of, or the target of increasing the high-speed broadband networks has been more focused on increasing firm productivity, employment, or other kind of targets, but not education. So they may provide new insights in order to implement policies such as subsidizing high internet packages or trying to increase the level of take-up. And because one of the value added of broadband investments and the importance of ensuring this universal access may mitigate important inequalities in educational opportunities. And this has been highlighted, especially in contexts such as the COVID-19 pandemic, in several papers that have recently published, showing that those students that didn't have online resources as powerful as their peers, they have suffered much more from this change between school environment to a 100% home learning environment. And basically, the extensions that we are thinking about this paper is that we want to try to understand a little bit better this home-school ICT interaction. So we find it quite interesting and cool. So we want to try to think about new ways of improving and getting more insights on that. We want to look at the effect on subject choices, so key stage 4, as Marcelo was suggesting before. And we would like to also to look at secondary school choices and see whether broadband has more effect on which school you choose through this information dissemination over the internet. So I think I'm on time, so thank you very much, everyone, for listening to me.
Perfect timing.
Hi, I have a question. Is that okay?
Okay, go.
Okay. I know that this is a very tough question that you're trying to answer, but I think that you don't have a theory or a causal relationship to link broadband speed to education outcome. And you do need that theory. Maybe you team up with some theoretician, but you do need a model here to be able to understand what you're doing, because you may be finding correlations, but you don't have a causal relationship. And you have to decide or explain how going from 100 megabits per second to 120 may be the same as going from 500 to 520. You may want to argue about that. And also, I think if I'm right, your data are pre-COVID-19. So you may also stress that and say something more. You really need, you say also that your results are economically meaningful, but meaningful of what? Of a demand? Is that a supply? What type of relationship are you estimating? And you have to know what type of relationship. And then I didn't follow the jump of 800 meters that you made in one of your graphs. I didn't understand what was that jump, why did that happen. Okay, thank you very much.
Okay, no, thank you very much, Teodosio. Bunch of questions. So I agree with most of them, some others not, let me tell you. So regarding the theory, you are totally right. We tried to do a model, but since we are mostly econometricians and empirics in our team, we just did some toy model we thought was a little bit embarrassing to show it to others, so that's why we didn't go further. But yeah, you are right. We may think about a model to explain the effect. It's a little bit difficult because since we cannot look at the mechanisms behind making maybe a structural model or theoretical model, we will not be able to calibrate the parameters mostly. Then the second thing you were arguing about, maybe you are thinking about non-linearity. So whether this 1 megabit increase is the same in each of the parts of the distribution. I think that's a great comment. That's one of the things that we want to extend. So we have the average treatment effect right now. We want to look at whether this 1 megabit, what is the distribution, right, of the effect, and look at whether increasing 1 megabit, if the already existing speed is high or low, it's different, right? Then other thing you were saying about the pre-COVID estimates, so you're totally right. So we put it into context on the paper, and basically since we have 2005, 2009. So one of the advantages of using data before 2008 is that in 2009, smartphones came to the market. And basically, smartphones, what it's going to do is that you're going to depend on the distance to a station. So you will have the smartphone at home, and the 3G technology, you can access internet everywhere. So this is going to kind of be to make our identification strategy more noisy. So this is one of the advantages, because now if you want to estimate the effect of home broadband, you have many confounding factors at the same time. So this is one of the advantages of having pre-2008 and pre-COVID data. What else more you were saying? You were talking about the jump. So this is basically what we use to estimate the causal effect. So we use that these students are living very close to the catchment areas. So one student is very close, but is covered by a larger distance cable. So it's going to have a lower internet speed, and the other is covered with a shorter distance cable, so it's going to have higher internet speed. So this jump is the difference between the speed that are going to be faced at the cutoff. And this is our first stage of the equation. So this is what's going to allow us to estimate our second stage. And I think I answered all your questions. If I'm correct.
Okay. Pepe. Hi, Pepe. Only a general question, general comment about the extension of the results in other contexts. I mean, I guess that these results are very focused on the technological context of the 2000s. It's very difficult to try to extend the result. Of course, only the general result about the relevance of the broadband access in terms of results, of student results. In that context, yes, but for example, currently, of course, there's no decay. The decay effect does not exist in fiber. So, of course, this closely related to DSL, but DSL is, for example, in Spain, is a small percentage of total number of broadband access currently. So I guess that it's very difficult to try to extend the magnitude of the effects in the current context. It's very, very difficult. And the second question, even in the context of I have a doubt because I know some numbers about the decay effects in Spain, for example, in the context of the DSL. And this really, I wonder if it's related to the architecture of the network, but they're pretty different. I mean, in Spain, the average distance to a local exchange is about 3 kilometers, but is in average, I mean. But the decay was much stronger than in your data. So I don't understand if it's related to the local the architecture of the network, of the telecom network in the UK versus Spain, could be, but it's a little bit different. It's like, yeah, even in that context, in that technological context. Thank you, Pepe.
Yeah, so first, Diego, super nice to hear from you. I'm very glad that to having you there. And yeah, I think these 2 points that you make are key on the paper. So the first one, let me answer about would be more, related to the external validity of the paper, right? So how can we extrapolate our results to learn something about the policy today? So you are totally right. There is one limitation and drawback, that is basically the fact that the online content nowadays is super different than the one that exists in 2008, right? So especially the social media. So at the time, Facebook or Twitter and these kind of online resources didn't exist. So this is social media type of Microsoft Messengers and other stuff that you could send messages. But the distraction is a little bit different today than what was used to be. But basically, that's the drawback, but then it has two positive aspects. And the first one is that these estimates are still relevant for a huge fraction of the world. So 14% of the world population has access to broadband nowadays. And then the average internet speed at the world level is about 7 megabytes. So it's quite close a little bit to the 5 megabytes that we are kind of estimating. So still our estimate seems to be relevant for a large part of the world that basically are developing this internet infrastructure, right? So we can learn something from that. But of course, I completely agree with you that it's quite difficult to make a comparison, especially for like developed countries in the situation right now. And then what you're talking about the decay, you're right, but the thing is like this ADCL technology has different technologies. So there is the DSL, ADCL 2+, and each of them has a different decay slope. So maybe that's one of the things that is important to mention. And then you were saying that, so basically this is the distance, it's about 2 kilometers. So it's a little bit different, distance to the station is a little bit different than the 3 kilometers that you were saying with respect to Spain. But I think this is about the distribution of the stations that were allocated maybe a little bit before and the distribution of the population. So here, regarding the jump, of course, here what we face is a trade-off between sample size and intensity to treatment. So if we take those segments that has very low or invisible, almost insignificant jumps, then we are not estimating any treatment, right? So what we do is that we define, I mean, our main sample has jumps with 300 meters and more, which is why you have this 900 that is basically a little bit higher than the 700 jump in the overall population, but you can see the standard deviation, so you can see that they are not very significant. And then what we do as our wasn't check is that we define our sample in different ways, and then if we take those jumps that are like very insignificant, our estimates gets really much more time, of course, because there is no treatment that is going to be. But thank you, those are great points, all of them. You have to think about how to answer on the paper.
Muchas gracias.
Andrés. Andrés, no se te oye. I think Andrés.
Sorry. I am back because I had a button pressed. Sorry. Yeah. So thank you very much for the nice presentation. I have just a couple of comments. The first one regarding the heterogeneous effects. I wonder if you could delve a little bit more into the effect by the previous grade in the exam, because you had just split in 2 parts. Maybe if you make 4 parts, you may find something which is like this availability actually increases inequality, right? Maybe this is an interesting finding, especially thinking on what you have just said, that around half of the world still doesn't have the access, right? So I don't know. I think you may have a research touch there, okay? If you maybe delve into this inequality relationship, which probably looks like it can be in the data, right? And my second concern is regarding the magnitude of the effect, right? Because you have this, let's say, this section, I think, maybe to try to, let's say, to argue that the effects are not low in magnitude, and maybe you go to the other extreme in the sense that the effects, looking to this last session, look super large in magnitude, larger than should be, right? And maybe this is because you are taking this 1 mega unit, okay, when it is very likely that this is non-linear at all. actually should be super non-linear. I mean, 1 mega from 7 to 8 is not the same as from 0 to 1, obviously, right? Or from 1 to 2. So I don't know if you may, when I was looking at the working paper while I was listening to you, and I was thinking that the effect was too small, but when I reached this last chapter, I said, no, it's too large, right? So I don't know if you can go to some place in between by, instead of saying 1 mega, I don't know, by another way to express it. I don't know if 1 standard deviation in internet success or something like this. I don't know. But this was my feeling. I don't know if the reviewers or somebody else had the same feeling. But thank you very much for the exposition.
No, thank you very much, Andres. I mean, all of what you say makes a lot of sense. So let me ask about first what you were saying about the previous, the pre-internet score, right? Yeah, I think you're right. I mean, we just like here, the thing is like with the RDs, it's very demanding. It's an empirical study that's very demanding in terms of observation. So that's why we just split the sample between both that are above the median and below the median. But you are totally right that we can try and split the sample into quartiles, for instance, of pre-internet, and see whether those that are very at the top of the distribution or at the bottom of the distribution that are heterogeneously affected. So I think it makes a lot of sense. So I just took note of it, and we're going to do it. That's very nice. And then the second thing, magnitude of the effect. Your intuition, I think, is good. I mean, what we compute here is the average effect, and maybe that's why it's quite seems to be medium size to large, right? Especially when we refine the estimates with the population of interest, and that's on our to-do list to do the more non-linear effects. So trying to see whether this is how is the distribution of effects over the different megabytes. So this is our to-do list. So I think you're right on that, and we want to try to dig it a little bit more. So thanks for your input.
Okay, thank you.
Rafa?
Okay, thank you very much for the presentation. And I don't know if what I'm going to say is going to make sense because I'm not familiar with this literature. But you said there is no theory behind it. But I think you may have some intuition, and I would like to hear the intuitions behind. And I probably think it is something which is related with the access. In this sense, one of the comments before about the non-linearity could be very, very important. For instance, if there is a problem of having access or not, the real interesting point is whether you just move from zero access to some access to the internet. And maybe there's a huge effect on that. And I don't know if you have any estimation about this effect of having just what is the real effect of having or not having access at all is my question.
Yeah, thank you very much, Rafa. Yeah, I think in that sense, what we estimate here is the effect of improving our broadband quality, let's say. So, like, condition on having internet, what is the effect of increasing your speed? But you're right that it would be nice to see what is the effect of not having internet at all and having broadband, because then the internet may be much larger. I mean, the treatment effect may be much larger. The problem that we have faced here is that from 2005 and 2008, we have all of the infrastructure developed, and basically the take-up was increasing exponentially over the years. So, I mean, I'm going to think about it and see whether we can do something about it, but that will be maybe something with a minor sample or something like this, because I mean, we have already like all the infrastructure developed when we are looking at it. But that's a good comment. So I will try to address this. Thanks.
Okay. Thank you.
Okay, I think that it's almost 2:20. I think that this was a nice discussion. I think that it's time for, I don't know whether there's another question, because you know that everybody's going directly. Okay, so I think that it's time for all of us open our mics and giving a standing ovation to Jose for that very, very nice presentation. And I think that we can keep talking with Jose for a while. Okay, so please. ¿Tenía mi micrófono abierto o no?
Oye, me ha gustado,
Sí.
Ah, menos.
Mucho mejor que las palmitas estas que salen en el...
Hace un feedback, ¿no? Un feedback loop aquí que...
se siente al público. Muchas gracias. No, muchísimas gracias a todos. Me ha encantado.
Tenemos un poco de
Gracias
rato
a ti.
todavía. No sé si queréis hablar un poco más, pero yo creo que ya está...